Okay, home plate for tonight says graph the following functions, and it's 6 of them. Copy these, please. A is y equals x squared plus 5x plus 6. B is y equals x squared plus 8x plus 12. C is y equals x squared minus 10x plus 9. D is negative x squared minus 3x minus 2 equals y. Then we got E is y equals x squared minus 9. And F is x squared plus 3 equals y. Copy those, please. Thank you. All right. So that's your home plate for tonight. It's 6 functions to graph. Okay. So to get us started, though, I do an intro to this next part of the algebra course to make sure that you know where it applies to. So, yeah, can you get the lights, please? There we go.
That's awesome.
So I'm going to start right about here. We've gotten on some of these before, yeah? No, it's barely going up. Here we go. And right. That was a good one. So it's very turning, So here we go. Okay, keep it down, please. Keep it down.
That's really scary.
Yeah, and especially because it locks there for a little bit. Watch, right there. Watch. He said loopy-loop. Look.
Wow. We had to do this all over again. I see a lot of water. Here we go.
Did he say skaloosh? No, he didn't say that. Alright, so I know. I wanted to introduce, get the right light, please. I wanted to introduce like this because to bring it to more the attention in regards to the design of it. So these are a couple of pictures that shows you some of the portions of roller coasters, right? So now check this out. These designs have a lot of mathematics. So for example, the first mathematics that I would use here would be graphing. So watch. Have we covered vertical lines? Yes. Have we covered horizontal lines? Have we covered positive slopes? You see all these positive slopes right here? And then negative slopes going this way? And so on and so forth, right? Same thing over here. Vertical lines, horizontal lines, positive slopes right here. We got negative slopes in the background. You guys see those back there in the structure? And so on and so forth. So if we were to actually do a design with graphing, we can actually design this entire ride. Except for, what is the one thing that we haven't really talked about?
Curves.
The curves, right? We covered everything else except for the curve. So for example, the curve on this roller coaster is actually the next section that we're going to cover here in math, in our algebra course. And you guys seen it before. Yes, I'm just showing you where some of the math is used. So who sees that this is the trajectory of that roller coaster, right? This is what we call parabolas in algebra. Parabolas. So you know what it's called? Parabolas. Now, where else do they use this kind of math? It's used also to look at the trajectory. Like if you've been to the beach, I don't know if you've been to those cruises where you see the dolphins like jumping next to the boat or whatever. The trajectory of a dolphin as it leaves the water and goes back in, that's a parabola. Do you guys see it? Yeah. Right. Or also, how about when you're throwing a football pass? You're throwing it from here. Yeah. And that ends on the other. So if I throw it from here and it ends over here, it's also a curved and it's also a quadratic function. So that's what we're going to be covering today. Also, back then in the medieval times, here, let me just give you a quick idea. Back in the day, there were these long tables at these kingdoms, and the king sat on one end of the table, right, in this huge chair, and then the guest and everyone else sat over here on this side around the table. But these were long, very long. They were actually so long that maybe it covered the entire section here for the 500 building. That's how long some tables were. So when the king had like festivities or whatever the case, he would invite people that were like from different kingdoms to come sit at his table and have either dinner or whatever the case. But then within those, there were spies. There were some that infiltrated that were spies that would want to go in and see what he had in his kingdom to see if they can come in later and attack. So in order for him to keep aware of what was going on, he would invite those people around his table, and then he had his architects or his engineers, look up please, create behind him a wall that was like this. What does that look like? A parabola, right? Doesn't it look about the same as the one we just drew right now? Now, why is that? Because this is how this works. Who's seen in homes these dish networks?
Oh.
Satellite dish? How the satellite dish works, it's a parabola. You guys see the parabola here? And the signal comes in straight down like this, and when it hits the dish, anywhere it hits, it bounces, the signal bounces, and it goes towards the center. That's why that is the receiver. It goes always towards the, doesn't matter where it hits on the parabola or on the antenna, the signal goes to the center. Well, guess what? Back in the medieval times, they understood that. So when people were talking about the king, oh, I see that they have all this and that, the voice that they projected, when like this, it hit the wall from any direction, and guess where it bounced to? To the center. And he was listening to all the conversations, like if it was so clear and crystal clear. Yeah, it's trippy how engineering is used to accommodate for different eras. So, what's that? Yeah, it kind of sounds fake, but believe it or not, it works. And this type of technology, they still use nowadays to create amphitheaters, like for operas and all that. Some amphitheaters, they're created like this, in a dome shape. Who's seen that? Because it keeps the sound and it keeps it going towards the center, so that whoever is at the center can hear it, or whoever's in the center speaking, people around can hear them crystal clear.
Mr. Q,
What a trip, huh?
is that why at theaters they have curved screens?
Yes,
Oh, okay.
screens. So with that said, that's a good introduction to quadratic functions. That's what we're going to get started with for this next module. So therefore, our objective, I can graph a quadratic function. Let's read together, 1, 2, 3. I can graph a quadratic function. So, what are quadratic functions? Let's find out. In your Fourier model, write that down. Quadratic function. A quadratic function is a function in y form in which the highest power of the variable is 2. A quadratic function is a function in y form which the highest power of the variable is 2. Examples: y equals 2x squared, or that one's also written as f of x equals 2x squared. Other example, y equals x squared plus 2, or f of x equals x squared plus 2. Also, y equals negative 3x squared plus 1, or f of x equals negative 3x squared plus 1. Non-examples, y equals mx plus b, y equals x cubed plus 9, and x squared equals y plus 5x plus 6. Copy that, and then I'll go over it in a little bit. So let me go over this definition for quadratic functions. Here it goes. It says, quadratic functions is a function in y form, so that's important, in y form. And the second part, the highest power is 2. Okay, so let's look at it. Is this one in y form or solve for y? Yes. The highest power is 2.
Yeah.
Same thing here, same thing here, okay? Now you're saying, Mr. Q, this one is not y. Well, it is y because instead of y, all they did is replace it with f of x. And in the past, who remembers what f of x stands for? That it is a function. That's what function stands for. But other than that, this is the same as y. Everybody understand so far?
Yeah.
Alright, so far we see that these are the same, right?
Yeah.
So now think about it. Why are these not quadratic functions? Talk it over with your neighbors, please. Why are these not quadratic functions? Alright, so this one right here, Michaela, why is this not a quadratic function? What did your neighbor say? There's no exponent of 2. And what is the requirement? It has to be 2. Okay, so far so good. How about this one right here? Robert. Why is this not a quadratic function? It has a 3 in the exponent instead of a 2. It needs to be a 2, okay? Thank you. This is the cubic. And this last one, why is this not a quadratic function?
Amanda.
Okay, go ahead, Yuvia.
Oh!
How about this one? Be nice. This one. Why is this not a quadratic function? It's an x squared, okay. So far so good, but why isn't it a quadratic function? It has to be solved for y. That's why it's y form and highest power is 2. So write that down, please, in your critical attributes. It needs to be in y form and the highest power is 2. Technically, this last one is a quadratic function, but from this point forward, I want you guys to think of quadratic functions already solved for y, and the highest exponent has a 2. Okay?
Wait, so that
So.
means, that's what I don't think, because you said the highest,
Power.
so it can't be, like, just x.
It can't be x, because if it's only x, what is the exponent on x?
1, but
1,
that's
so...
alright, because I was confused as to the highest.
It's the highest and least. Right, Mr. Q?
Alright, so here we go. So with that said, let's go to steps. Copy these 5 steps only. Only 5 steps. Number 1. Step 1. Make sure the function is in y form or solve for y. Step 2. Build an input-output table and add a domain of -2 to 2. Step 3. Substitute the values into the function and find the range. And what is the range? All y values, right? Step 4, plot order pairs on the graph and function. Plot the order pairs and graph the function. And step 5, check if a given point is on the function by substituting. Copy that, please, and then we'll go over an example. So once again, steps. Number 1, make sure the function is in y form or solve for y. Step 2, Build an input-output table with a domain from -2 to 2. Step 3, substitute the values into the function and find the range, which is all the y values. Step 4, plot your order pairs and graph your function, and at the end, check one given point to see if it's on the function by substitution. Are we there? All right, so on your big graph, get your big graph in front of you. On the top left corner, copy this down, example number 1. Example number 1. And cover the steps so that you guys can focus on the instructions. So it says, number 1, graph y equals 2x squared and check 2, 1 is on the function. So we're going to graph y equals 2x squared and check to see if 2, 1 is on the function. So, step 1. What is step 1, everyone?
Make sure the function is in Y form.
Is it in y form?
Yes.
Yes, so we don't have to worry about it. So what would be your immediate second step as you're graphing?
Build an input-output.
So let's do that together. Input-output table would be x and y, and for the x values we're going to use -2, -1, 0, 1, and 2. Yeah. All right. Then let's rewrite this equation. I'm going to take the equation, and instead of x, what do?
You input it.
Write a parentheses, right? Because that's where we're going to input the values for x. Okay. So here we go. So our first value that we're going to substitute is what? -2. So that goes in here. So be careful with this one though, because now we have an exponent, and we always, if we follow order of operations, what would be our first step? Exponent, right?
Yeah.
So what is -2 squared? It's -2 times -2, that's positive 4. So this is y equals 2 times 4, and y equals 8, and that goes right there. So let's plot that point, -2, 8, -2, 8 is up here. Plot that and write your coordinate. Okay, let's rewrite it again, the equation, but instead of x, open up parentheses so that we can substitute the next value. The next value would be -1. So what is -1 squared? -1 times -1 is positive 1. Positive 1, so this would be y equals 2 times 1, and that is 2. So my value should go right here. So let's plot this point, -1, 2 is about right here, and write your coordinate. There it is. Rewrite your equation again, but open parentheses for the next value, which is 0. Is that correct? What is 0 squared? And what is 2 times 0? So therefore, that goes right there. So therefore, my point 0, 0 is right here at the point of origin. You plot that, and you write your coordinate. And finish the last two by yourself. Go. All right, and the last two values, we substitute 1 in there. 1 squared is 1. 2 times 1 is 2. That goes here. 1, 2 is about right there. Write your coordinate. And the last value we substitute is 2. So 2 squared is 4. 2 times 4 is 8. And 8 goes here. And my last point is 2, 8, which is up here. And my coordinate is 2, 8. Are we there so far? So now before I graph my parabola, look up please. Let me take you back to graphing again. We always go from left to right, is that correct?
Yeah.
So the first point that comes up from left to right is this one.
Yeah.
You might be tempted to use this one, but from left to right, the first point is this one.
Yeah.
And if we're on the roller coaster, that means that we're up here, and it's going which way? Down, and then it's going to curve back up, and it goes up. Boom. That's pretty cool, huh? You don't need a ruler.
It's curved.
That's why it's a curve. All right. So Now that we have our first part, it says graph y equals 2x squared, and then check if 2, 1 is on the function. So this is what we're going to do for the next part. For the next part, we're going to write the equation again, but instead of writing y, hold on, we're going to use these values. What is y? 1. And what is x? 2. That goes over here. Does everybody see that? Here's my equation. I substitute those in there. Do that yourself so that you can follow along. So what is 2 squared? 2 squared is 4. Bring that down. What is 2 times 4? Is 1 equal to 8?
No.
So then we're going to write not on the function. What's another way of checking to see if a point is on the function if we're graphing?
Just look.
Plot your point and see if it's on the graph, right? So let's plot this point. 2, 1. Where's 2, 1 at? 2 of x, 1 of y. It's right there. Is it on the function?
No.
No. So therefore you just write not on function.
This is cute, so it could be.
Hold on. Yes?
This is cute. So it could be like half, like, so it could be, like, it could be 1, I mean, it could be half x, 1 y.
Half x.
Yeah, so that's on the grid.
Oh yeah. Like whichever point that is on the graph, it is on the function, and I'll show you another point right now.
Okay.
Here we go. So this is what Taylor was saying. Look up, please. He's saying, Mr. Q, if I was to place a point right here, let me zoom in so you guys can see that point. What is the value of x here? It's about 1/2, right? And what is the value of y right there? 1/2. So that, it's not 1, 1 is up here, right?
Oh, no,
So therefore that coordinate is 1/2, comma, 1/2. Everybody see that? So by graphing it, we can actually see that it is on the graph. Okay? So, any questions on what we're doing?
No.
Okay? And basically this is a home play.
Are you?
Yeah, that's it.
Isn't that on
Let's-
the worksheet we got last time?
No.
Oh, I thought I saw it.
It's very similar. Turn your paper over in the back, see if you can do this one by yourself. Copy this one, example 2. It says y equals negative 2x squared. So it says graph y equals negative 2x squared, and check to see if 1, 1 is on the function. So, everyone, what is our first step? Check to see if it's in y form. Is it in y form?
Yes.
Yes, so we don't have to worry about doing anything to the equation. So what's our immediate second step, Taylor B? The table. So therefore, what is our domain for the table? From negative 2 to 2. Very good. And once again, you're going to write your equation, and instead of x, you open up parentheses, and that's how you're going to substitute values in there, right? This one is negative 2x squared. So, finish your table, plot your points, and graph your function. Go. So here goes the values. Let's see. We substitute negative 2 in here. That's negative 2 squared is positive 4. And then we have y equals negative 2 times 4. That gives us negative 8. So our first value is negative 8. Hands if you got that. Okay, so this is negative 2. Remove this. But now negative 8 is down here. The next value. Here we go. The next value, you should have gotten negative 2. And that one is negative 1. Negative 2 is about right there. From there, the next value we substitute is 0. We know 0 times 0 times 0 times 0 is 0. So that is our point of origin, which is right there. And the next one, value is 1. 1 squared is 1, so that means negative 2 times 1. What is negative 2 times 1? Negative 2. So that goes right there. And that point is 1, negative 2, which is right there. And the last value should be negative 8, is that correct?
Yes.
And that is also down here, 2, negative 8. There it is. So now, once again, reading it from left to right, what is my first point from left to right? Negative 2, negative 8. So if this was a roller coaster, now it's going which way? Up. So it's going to go up, and it's going to loop, and then it's going to go... Everybody see that? All right. Hands of your graph looks like that. Okay, good. So you see how, since we already did plenty of practice with graphing for the first semester, now it's just transferring to this. Does that make sense? Yeah, right? So, yeah.
What if we did negative 5, negative 4, negative 3, negative 2, negative 1 for the x's?
Okay, but what domain am I asking you to use? From negative 2 to 2.
Okay.
Okay? So, with that said, let's check to see if that point is on the graph. So instead of y, what number do I substitute for y? 1, and then for x, 1. So this is 1 equals negative 2. 1 squared is 1. Is 1 equal to negative 2? No, so it's not on the function. And we can totally see it if we plot the point. Where's 1, 1? Right here. Is it on the graph? No. Any questions? No? So now, let me show you a couple of things to see if you see what I see. Here we go. Look up. Okay. Look at the first example that we did. Look at the coefficient of x. And look at the direction of this parabola. Don't say it out loud if you see it. Hold on. Now look at the coefficient of this one, and look at the direction of this one. Talk it over with your neighbors. What is it that you see? Okay, let's see. Who can give us a good, like a good rule? Verbalize it. Devin.
No.
Close. White.
Negative.
Hold on. Let me get you started. When the coefficient of x is positive, what?
When the coefficient of x is positive, the parabola is up or like.
When the coefficient of x is positive, the parabola opens up. And when the coefficient of x is negative, the parabola opens down. Who sees that? Or a good way to remember, check this out. Whenever the coefficient of x is a positive, it's like a happy face. Do you guys see how this person is happy? However, if it has a negative, then the person is...
Because it's feeling negative.
Oh.
No.
So, give me a second. Just really quick. All right. So for home plate tonight, once again, you have 6 equations to graph, which are I showed you at the beginning, which are right there. So you have 6 of them to graph. That's why you're taking extra graph paper, right?
Yeah.
All right. Have a good one, guys. Enjoy your home play. I see you guys. Tamales.